Jai Hind everyone. Myself Dr. Pankaj Goyal, Assistant Professor in the EC Department at AKGEC Engineering College. Today we'll have another important topic for discussion, that is metallization, properties and deposition processes. The content that I'm going to cover today is introduction of metallization, desired properties of metallization, metallization applications, and what is ohmic contact, what are the advantages of aluminium as a metal, and what are the drawbacks of aluminium as a metal in VLSI. Then deposition processes that we use in metallization, and then a specific deposition process, sputtering PVD process, and electroplating, and in the last, references. So as we know that in case of VLSI, to prepare a VLSI chip, there are different processes that are used. So one of the important process that we use is known as metallization. As we know that our VLSI chips consist of millions of transistors, and all those transistors need to be interconnected with the help of a conducting layer. So for that interconnection of different transistors on a IC, we have to use metallization. Also, as we know that in case of VLSI ICs, we generally use FETs, MOSFETs, field effect transistors, in which there are three terminals: drain, source and gate. So these terminals, they are on a semiconductor wafer, and these terminals are to be connected to the other transistors or the outside world with the help of metal contacts. So metallization is an essential process in VLSI design. In this figure, we can see that our MOSFET consists of three gates: source, gate and drain. Here all the three terminals, source, gate and drain, a contact is made here with the help of metal. Now, the central region in this figure is known as the gate. This is our gate, and please also note that this gate contact is different from source and drain in a sense that there is a dielectric layer here in between the substrate and the metal. There is a dielectric layer, SiO2 layer, silicon dioxide layer, whereas our source and drain are directly in contact with the metal. So that is the difference between gate contact and other two contacts. Okay. So here the central region is gate, and here the substrate silicon is isolated from the metal electrode by an insulating layer. And here we use a polysilicon layer for the gate electrode, and it controls the working of the MOSFET as an off or on switch. The work function of the metal here plays an important role in determining the voltage required to activate the device. So work function of the metal here plays an important role. It tells the amount of voltage that is required to switch on or switch off the device. The other two contacts are known as source and drain. And for these two contacts, aluminium is used. Aluminium metal is used. For gate electrode, polysilicon is used. For other two contacts, that is source and drain, aluminium is used. And here, the work function of the metal that we use for source and drain is used in determining the current flow characteristics in these regions. As we know that the current in a MOSFET flows from source to drain between these two terminals, source and drain. So the work function of the metal contacts, aluminium that we use, plays an important role in determining the current flow characteristics. Now let us see the desired properties of metallization for ICs. Low resistivity. The resistivity should be low. Easy to form. The metal layer that we have to put on a IC, it should be easy to form a layer of metal. Second, it should be easy to etch for pattern generation, because at the undesired areas where we don't need metal, we need to remove it or etch it. So it should be easy to etch also, easy to form as well as easy to etch. Then it should be stable in the oxidizing ambient. It should not oxidize. It should be mechanically stable, good adherence with the wafer, and low stress. So these are the desired properties. The surface smoothness. The surface should be smooth. And as we know that there are a number of processes that we do on a IC. So the process may be involving high temperature process, or it may be like dry or wet environment, dry or wet ambient, like dry or wet oxidation. In all these ambients, our metallization should be stable. So that is a desired property, that it should be stable in different processes. Then another property is that it should not contaminate the devices, wafers or working apparatus, because contamination lead to defects. It should have a low contact resistance, minimal junction penetration, and low electromigration. So all these are the desired properties of metallization for ICs. Now, the next topic is metallization applications. Here we can see the primary metallization applications can be divided into three groups: gate, contact, and interconnects. As I just told you, that interconnection is nothing but the connection of different transistors with the help of a metal layer. That is interconnection. And interconnection involves aluminium polysilicon material that we use for interconnection. Polysilicon has been the form of metallization for gate as well as interconnection. Now, here, when we talk about contact, we are talking about source and drain contact. Source and drain, they are known as contact because in this case, the substrate is in direct contact with the metal layer. So all metallization directly in contact with the semiconductor is called contact metallization, and here we are using aluminium. Now because for gate and interconnection we use polysilicon material as a metallization. So here the metallization plays two important roles that we need to remember. The first one is that it controls the speed of the circuit by virtue of the resistance of the interconnection runners. Here the resistance of the interconnection runners is denoted by the sheet resistance, and the parameters that affect the speed is number one, sheet resistance, secondly, the length of the runner, and the third one is oxide thickness. So these are the parameters that affect the speed of the signal that travel on these metallization layers. The second property of metallization is flat band voltage. As we know that the metal and the semiconductor, they have a different work function. Now, to counterbalance that, the work function difference between the metal and semiconductor, this metallization is used. A flat band condition is maintained. This is our metal, this is our substrate, metal and substrate, and there is a work function difference. Here, with the help of the flat band voltage, the work function difference is counterbalanced. The next topic, after we have discussed the primary applications of metallization, that is for gate, for source and drain contacts, and interconnection. The next topic that we are discussing is what is ohmic contact. It's a very important topic that we have to understand, because when metal comes in contact with the semiconductor, there are two kind of contacts that can be formed. One is known as ohmic contact and other one is known as Schottky contact. The ohmic contact is one which follows the Ohm's law, in which current can flow in both the directions, from metal to semiconductor and from semiconductor to metal. Whereas in case of Schottky contact, it is a rectifying contact where current can flow only in one direction. So here the purpose of metallization is to create an ohmic contact so that the current can flow in both the directions. And for that, a very important property that we have to maintain while making a contact, while making a metal contact, is the work function of the metal is smaller than the work function of the semiconductor. So if the work function of the metal is smaller than the work function of the semiconductor, where we have here considered the N-type semiconductor. So if this property is true, then we will have a ohmic contact. And if this metal work function is greater, then it will be a Schottky contact, rectifying contact. Okay, so we have to keep in mind. So ohmic contact is a non-rectifying junction. Non-rectifying means the current can flow in both the directions, and which has a low resistance and provides current conduction from metal to semiconductor and vice versa. A good ohmic contact is usually formed by depositing a metal on the semiconductor, and it does not perturb the device characteristics and is stable both electrically and mechanically. Now, some of the other properties or applications of metallization are the Schottky barrier contacts, guard rings, and the diffusion barriers. So these are some of the secondary applications of metallization. Those three were primary applications: the gate connection, source and drain contact, and the interconnection. Those were the primary applications, and these are the secondary applications. to create a Schottky barrier, to create a guard rings and diffusion barriers. Now let us discuss in brief about these. A Schottky barrier, named after German physicist Walter Schottky, which is also known as a Schottky barrier diode or a hot carrier diode, is a semiconductor diode formed by the junction of semiconductor with the metal when the work function of the metal is greater than the work function of the semiconductor. Now, what are the properties of this Schottky diode and why it is useful? Is that, as we know that in case of a silicon diode, the voltage drop of 600 to 700 millivolt, that is 0.6 to 0.7 volt in forward bias is observed. Whereas in case of Schottky diode, in case of forward bias, a voltage drop of only 0.15 to 0.45 volt is observed, and it leads to higher switching speeds and better system efficiency. Guard rings. Now guard rings, as the name suggests, these are the rings that are created to prevent the undesirable interconnection between the devices or circuit, subfunctions and power domains. The guard rings prevent both current injection and potential perturbations that can lead to parasitic devices and electrostatic discharge failure and latch up. So guard rings are used to prevent the flow of current between different regions. Here we can see, because we have different wells in our ICs such as N well and P well, and the parasitic effects that develop due to different wells, that can cause unwanted coupling. And this unwanted coupling create parasitic effects, parasitic capacitances, which is undesirable. Similarly, electrostatic discharge can damage the dielectric in IC. So electrostatic discharge should be limited or avoided. And all these work can be done using guard rings. Now, another important parameter is latch up, which is basically a short circuit between the power and the ground rail. And if there is a connection between the power and the ground rails, then what happens is it can lead to damage of the circuit. So this kind of latch up, undesired connection between the power and ground, it should be avoided, and it can be avoided using guard rings. Now, diffusion, another application of metallization is diffusion barriers. Barrier layers such as tantalum, nickel and nickel chromium are used to prevent the diffusion and reaction in metallic systems. We know that when we do any process at a higher temperature, diffusion happens. Diffusion of the impurities from higher concentration region to lower concentration region. And if this diffusion is undesired, then it have a bad consequences for our IC. It can lead to poor IC design, poor IC outputs. So it should be discouraged and it should be avoided. And it can be avoided if we use the diffusion barriers. The diffusion barrier is nothing but some of the metals that we use which can create the compound. When diffusion happens, now those impurities, when they come in contact with the metal, they make compounds. And diffusion stops there. It doesn't pass through the metal layer. And it reduces the diffusion rate. Okay, now let us sum up about the metallization applications, as there are several other applications of metallization for ICs, and none of the metal none of the metal, it is important to note, none of the metal satisfies all the desired properties. As preferably we use polysilicon and aluminium for metallization. Even aluminium suffer from a drawback of low melting point. And also we have to note that the metal film, which is at the top layer and is a thick layer, it should also act as a corrosion resistance coating for protecting the active devices, that is a transistor, that are beneath the metallization layer. So this metal layer should also act as a corrosion resistance coating. Okay, some of the metals that may be used in various applications, we may note here. For a top level, we may use aluminium. As a diffusion barrier, we may use nitrides, carbides, borides, titanium, tungsten alloy, silicides. For gate, interconnect and contact, we generally use polysilicon, aluminium, silicide, nitride, carbide for specific applications. Some of the other metals that we can use in metallization is molybdenum, tantalum, tungsten, niobium, zirconium, hafnium, platinum. So these are the different metals that we may use depending on the requirement of metallization. Now, what are the advantages of aluminium? Why we are preferring aluminium for metallization? Number one is the ease of processing. It is easy to process aluminium, that is why it is preferred. Second is aluminium's ability to reduce the native silicon dioxide. So this is a desired property, because we know that we always have a dielectric layer on the surface, on the wafer surface, and if aluminium has the ability to reduce it, it is a desirable property. Then it has a low resistivity, that it is highly conductive, so which is a desirable property. So these are some of the desirable properties of aluminium, why it is preferred. Now in the next slide here we will see what are the disadvantages of aluminium. As we discussed, it has a low melting point, that is one of the drawback, and the second drawback is that it has undesirable electromigration behavior. Electromigration behavior is nothing but the movement of atoms based on the flow of current through a material. So this electromigration behavior is undesirable. So these two are the main drawbacks of aluminium. Now next, move to the deposition processes. For metallization, deposition, we can classify the process into two types: chemical vapor deposition and physical vapor deposition. Chemical vapor deposition process, we have also discussed it. We are also using chemical vapor deposition for the deposition of polysilicon material or other layers, other kind of layers like SiO2 or nitride layers. Physical vapor deposition, the second process that is mentioned here, is specifically we use for metallization. Okay. Now let us quickly discuss the two processes. First one, the CVD process. The advantages of CVD is excellent step coverage, large throughput, low temperature processing, and tungsten, molybdenum have been successfully deposited using LPCVD. LPCVD is a low pressure CVD process. Actually, there are three kind of CVD processes: low pressure CVD process, ambient atmospheric pressure CVD process, and the plasma enhanced CVD process. Okay. So there are three CVD processes. Now, what about PVD? Now, in PVD, there are two processes. One is evaporation and the other one is sputtering. And in both the processing, the steps that are involved in the deposition of a metal there are three steps. First one is converting the condensed phase into a gaseous or vapor phase, transporting the gaseous phase from source to substrate, and the third is condensing the gaseous content on the substrate. Let us see here. This is the evaporation PVD process. In evaporation PVD process, here this is our source which is at a high temperature converted into vapor form. Here heating, resistive heating can be used, and this solid source is converted into gaseous form, vapor form, and those vapors are taken to the wafer, the silicon wafer, where they are deposited. So this is evaporation method, PVD. This is second kind of evaporation method, in which instead of resistive heating, we are using electron bombardment. Here, with the help of a filament, the electrons are bombarded on a particular target, and the vapors from here, then they go back, they go to the silicon wafer for deposition. And the advantage of this E-beam evaporator is that the high melting point metals can be deposited, because we don't need to raise the temperature at a lower temperature. Also, with the help of electron bombardment, the metals, the solid metal can be converted into vapor or gaseous form, and those vapors are taken to the silicon substrate for deposition. And here another important advantage is the contamination is minimum, because there is only local melting of the source. Local melting of the source. In the previous one, when the filament is heating, in addition to this source, the nearby equipment also may generate the vapors which contaminate the system. The next is sputtering process. Sputtering is a PVD process in which ejection of atoms occur from a solid target by high energy ion bombardment. Here, for ion bombardment, we are using inert gas. We are using inert gas molecules, atoms, and these inert gas molecules bombard the target substrate, target material, which is solid. And when these inert gas molecules target this solid material, then the vapors are generated, the ions are generated, and those ions are transported to the substrate, where on the substrate it get deposited. For this, we may have a radio frequency, DC and DC magnetron sputtering processes that may be used. Radio frequency sputtering is the one which use alternating current, AC current. Okay, whereas the direct current, and we use DC and DC magnetron sputtering techniques, we use DC current. Sputtering is carried out at relatively higher pressures, It is a physical process and it causes the damage. Because when ions are bombarded, so it causes damage. And this damage is need to be removed by the annealing process. This is the schematic diagram which shows that how the argon inert gas ions bombarding the target material, solid target material, and from there the ions that are sputtered from that place, they come down to deposit on the wafer. Here at the wafer surface, deposition takes place. Deposition of these dopants which are coming from here, this target, with the help of these argon ions. And here in case of magnetron sputtering process, a magnetic field is used which used to ionize the gas in front of the target, and it lead to better deposition rate and greater contamination control. So the last one is electroplating deposition technique. In electroplating deposition technique, we need a seed layer. We need a seed layer on which more metal layer can be, more thicker metal layer can be deposited with the help of electroplating. So here, first, with the help of a sputtering technique, we create a seed layer of 30 to 200 nanometer thickness, and then using a bath, rest of the metal is deposited on the seed wafer. The reaction that is involved is this one, where at the anode side we have a copper ions, and then these, when in the bath, these copper ions react with the water molecules and we get the copper atoms which get deposited on the cathode. This is our wafer. End of today's topic. The books that I have referred are SMZ, VLSI Technology from McGraw-Hill Education, and the second one, Saurabh K. Gandhi, VLSI Fabrication Principles, While India Private Limited. Thank you.